Okay, so new chapter today, chapter 7, is based on a new class of functions called exponential functions. Okay, throughout pre-calculus, you guys have been learning about different kinds of functions. The very first one you ever learned about was lines. Okay, in grade 10. Then you learned about parabolas and quadratics in grade 11, and you learned a little bit about rational functions. Grade 12, you learned about trig functions, radical functions, polynomial functions. And now you get to learn about the wonderful world of exponential functions. Okay, these guys are most popular when you study things like population growth of either bacteria or just like ducks or dodo birds, or I guess you can't study them anymore because they're all dead. Ha! Okay, or beetles or anything, any kind of organism. You study its population growth over a series of years, likely you're going to be dealing with an exponential function. Also, if you have like a solute and a solvent, chemistry flashback, what does that mean? What's a solute versus a solvent? Yeah, good, right? The solute is the thing that you put into the thing to dissolve it, and the solvent. So like salt in water, salt would be the solute, water would be the solvent. Yeah, water is kind of amazing because it's like a universal solvent, except for like oil and things like that. But anyways, you can monitor the concentration of that solute, especially if you're like studying the concentration of a drug in a bloodstream. So you can tell like patients how many pills to take at so many hours so that their concentration of that drug stays at a reasonable level so that it helps cure them from whatever's killing them or hurting them. Or if you're studying like a contaminant, that's a hard word to say, contaminant. Oh, I got it. I even spelled it wrong. Contaminant. That's why they did autocorrect. I was like, that's spelled right. Okay. In a lake or a river, okay, you can monitor the concentration of that contaminant over a period of time, especially if you're trying to flush it out. You can figure out how long it'll take to get rid of that contaminant. Exponential functions will do that. And also, RRSPs, yes, you can model the growth of an RRSP exponentially if it still follows the same behavior that it has always been following. And radioactive decay of isotopes. Do you guys know about that? Half-life? Okay, that weird phenomenon where it just like becomes half of its mass over a certain period of time. Blows my mind, yeah. Radioactive decay of isotopes. The chapter after this, we're going to study the evil twin of exponential functions, or the best friend. I like to think of it as the best friend, but I call it the evil twin because they can be a little bit difficult. Logarithms. Ah! Dun dun dun. Just got a bunch of blank stares, okay. So, big question, how do you know you're dealing with an exponential function? Right? You know some indicators for quadratics, you know indicators for radical functions, and so on. How do you know you're dealing with an exponential function? Okay, exponential functions have a variable in the exponents. That's what goes in that blank there. Okay, they have a variable in the exponents. Okay, so just to give you some examples, a really basic one would be like y equals 2 to the power of x. Okay, that's a really basic example. Another one could be y equals 1/3 to the power of x. The half-life formula is n equals n naught 1/2. What is it? T over h, I think. Yeah, I'm pretty sure that's the half-life formula. Okay, where you have n naught is a parameter. That's the initial mass that you start with. Half-life is also a parameter. It's based on what isotope you're talking about, and t is the variable here. Okay, and it appears in the exponent, so therefore it's an exponential function. That kind of tells you exponential means that there's a variable in the exponent. Maybe that's a good way of saying it. Another popular one. This is my favorite finance equation. Whoops, and I already messed it up. A equals P times 1 plus I over C to the power of n times C. This is like my favorite finance equation. It tells you how much an investment is worth after a certain period of time, given how much percentage is growing and when it's compounded. Because that sounds a little complicated, but it helps you monitor the growth of your stuff. That's a good way of saying it.
Business class.
And you can also do it for loans, too. It can help you figure out how much your loan is going to be at after so many months. So it's very, very, very useful. I use it all the time because I'm like obsessed with personal finance. So you guys know that. Yeah. Okay.
Wait, math is actually useful?
Yeah. Who would have thought? Okay.
You can use it.
Write this guy down. This is the general form for exponential functions. Y equals c to the power of x, where obviously x is your variable, but c is just like, c is some real number. Okay? So you've got y equal to something raised to a variable. Maybe that's a good layman's terms way of saying that. But yeah, the big indicator of exponential functions is this guy, having a variable in the exponent. That should communicate to you right away that you have exponential functions. Okay, so example 1 studies the behavior and the shape of exponential functions. Linear graphs are what shape? They're straight, they're lines. Okay, quadratics are parabolic, or humpy, or not humpy, valley-like. I forgot absolute value functions. Those are like pointy.
Like these.
Right? Maybe I should draw these. So linear, quadratic, and then there's absolutes. They're pointy like that. There's radical functions, which looks like, what did I say? I said something funny. Like half parabolas that got beat up and left for dead. Because they're like parabolas laid sideways, but there's only half of it. Okay? They're actually inverses of parabolas. Yeah, they're cut in half. Trig functions are like the waves of an ocean, which sounds very poetic and cheesy, but it's true, with the exception of tan. And exponential functions are like really, really, really scary roller coasters. Okay, like that. Like that's why I showed you that video. Okay, so they look like this. Okay. Oh, that's bad. I use red. Okay, they go up like that, and then you go off to your death. Okay, that's actually a pretty gradual curve. They usually come like this, and they grow very quickly, or they die very quickly. Okay. Well, I mean, it depends on what parameters you have in your equation, but they have this basic shape, like a very, very scary roller coaster. If you were on this with some of your friends, that would be. Yeah, good times. Take your girlfriend there. That'd be awesome. Yeah, right? Have the hair flying off the back. Okay, why not, eh?